Hey, welcome. We tend to think that simple things should act in simple ways. But what if I told you there's this hidden world of incredibly complex, almost unpredictable behavior hiding inside systems we thought we had all figured out? Today, we're going to pull back that curtain. So let's start with a bit of a puzzle. What on earth could a big, churning chemical reactor and a tiny little electronic diode possibly have in common? I mean, they seem like they're from completely different universes, right? Well, as we're about to see, they share a really surprising, deep connection. But before we can get to the weird and complex stuff, we have to start with the simple. So let's first take a tour of the predictable, orderly world of what we call linear systems. This is where all the rules are straightforward and everything behaves exactly as you'd expect. Now, the absolute key to this linear world is something called the superposition principle. It's actually a pretty simple idea. The whole is exactly equal to the sum of its parts. Nothing more, nothing less. Think about two ripples in a pond. Their combined effect is just, well, the two ripples added together. The response you get is always directly proportional to the input you give. And this principle gives us two really predictable properties. First, what we call homogeneity. If you double the input, you get exactly double the output. Simple. And second, superposition. The effect you get from two inputs acting together is literally just the sum of what each would do on its own. It's this rock-solid predictability that makes linear systems so easy to work with. And this image, this phase portrait, really visualizes that predictability perfectly. See how all those little arrows, which show all the possible paths the system could take, they all lead to one single stable point. It's kind of like a marble in a bowl. Doesn't matter where you start it, it's always going to roll down to the very bottom. There's only one possible ending. Okay, but what happens when systems just don't follow these rules? That's where we crash into the world of nonlinearity, which, it turns out, is a much, much better description of the world we actually live in. So what is a nonlinear system? Well, it's basically any system that breaks that superposition principle we just talked about. In these systems, the whole is not just the sum of its parts. Here, doubling the input might quadruple the output, or it might do nothing at all. The old rules are out the window. A perfect everyday example of this is saturation. Just think about the volume knob on your stereo. At low levels, it's pretty linear. You turn it up a little, the sound gets a little louder. But once you crank it to the max, that's it. It doesn't matter how much more you turn that knob, it's not getting any louder. The output is no longer proportional to the input. The system is saturated. And boom, that's a nonlinearity right there. Now, when systems break free from these nice linear constraints, they can start producing entirely new kinds of behavior, phenomena that are just impossible in a linear world. And you'll see that this isn't about things going wrong. It's about the system revealing its true hidden complexity. So, what are we talking about here? Well, nonlinear systems can have multiple different stable states, not just one. They can generate their own self-sustaining oscillations or rhythms. They can exhibit chaotic motion that looks completely random but is actually deterministic. And they can make these sudden, dramatic jumps from one state to another. Our main tool for actually seeing all this is the phase portrait. Think of it like a map. Each line on this map represents a possible journey the system can take over time. By looking at the whole map, we can understand exactly what the system's going to do, no matter where it starts. And this just illustrates the difference so perfectly. On the left, there's our predictable, linear-like system again, where everything just collapses to a single boring point. But on the right, that's the phase portrait of a frictionless pendulum. It doesn't settle down at all. It gets locked into this endless repeating dance. This is a fundamentally different and way more interesting kind of behavior. That repeating loop has a name. It's called a limit cycle. It's a self-sustaining, stable oscillation. And what's so wild about it is that the system is drawn to this oscillation. It doesn't matter where it starts, it will eventually spiral into the exact same repeating loop, with a fixed amplitude and frequency that's determined by the system itself, not by its starting point. This image shows the concept beautifully. See? If a path starts inside the loop, it spirals outwards towards it. If it starts outside, it spirals inwards. The limit cycle acts like this dynamic attractor, like a racetrack that the system is just destined to run on, forever. And this isn't just some abstract math idea. This phase portrait right here, it describes the actual behavior of that chemical reactor we mentioned at the very beginning. That loop represents a self-sustaining oscillation between the concentration of the reagent and the reactor's temperature. It heats up, the reaction speeds up, it uses up the reagent, then it cools down, the reagent builds back up, and the cycle just repeats, on and on. That's a real-world limit cycle in action. So, some nonlinear systems can settle into this endless rhythm, this oscillation. But that's not the only trick up their sleeve. While our linear system had only one stable home, other nonlinear systems can offer a choice of destinations. A system could be perfectly happy sitting in several different states. And this brings us back to our simple little diode. On this chart, that curvy line represents the diode's electrical behavior, and the straight line is the rest of the circuit. And where they cross, we find a stable equilibrium point. But look, they don't cross once. They cross 3 times. So we have 3 possible equilibrium points, Q1, Q2, and Q3. Now, when we look at the phase portrait for that diode circuit, it reveals something amazing. Of those 3 points, only 2 of them are actually stable. That one in the middle, Q2, is unstable. It's like trying to balance a marble perfectly on top of a hill. The slightest little nudge, and it's going to roll away. So, depending on its starting voltage and current, the system will always end up in one of 2 different stable states. Its final destination depends entirely on its history, where it began its journey. Okay, so we've seen these self-sustaining oscillations and systems with multiple possible futures. But what's the big picture here? Let's tie this all back to our original question and see why this is so important. So, what do a chemical reactor and a diode have in common? The answer is nonlinearity. They both throw the simple rules of proportionality and superposition out the window, and that allows for these much richer, more complex behaviors to emerge. One settles into a stable, oscillating limit cycle. The other can choose between one of 2 stable resting states. They're both speaking the language of nonlinear dynamics. So, let's just quickly recap. Linear systems, they're predictable because the whole is just the sum of its parts. Easy. But nonlinear systems break that rule, and in doing so, they create a whole universe of unexpected behaviors. Things like limit cycles and multiple stable states. These are real phenomena you can find everywhere. And the most important part? This stuff isn't random. It is the underlying language of how the real world actually works. And that leaves us with a final big question to chew on. If a system as simple as a diode circuit or a basic chemical reaction can hold this much surprising depth, multiple futures, self-sustaining rhythms, just imagine what hidden complexities are waiting to be discovered in the truly massive nonlinear systems that govern our lives. I'm talking about things like the global climate, or financial markets, or even the human brain. What are they hiding from us?